Dear students, welcome to Environmental Process Systems, Tutorial 7. Let us now take a look at question 1. A 12-meter cube combustion chamber in a power plant is generating ozone at a rate of 0.3 moles per hour. Simultaneously, ozone decomposes via the following first-order reaction. The rate constant for the depletion is given as 0.22 per hour. Fresh air is flowing into the combustion chamber at a rate of 20 liters per minute, and air from the combustion chamber is flowing out at the same rate. You are supposed to determine the steady-state concentrations for ozone in the combustion chamber. So what you need to do first is to create the mass balance equation. So with your mass balance equation, you can now have your appropriate assumption, which is at steady state. So your dNA dt will be equals to 0. So with that, you can then input the variables that you know into the equation. So Q in is given as 20 liters per minute. Concentrations in, because it's fresh air, so we assume it to be 0. Let's put it in terms of moles per liter, minus flow rate out from the combustion chamber is similar to the inlet, so it's equals to 20 liters per minute. Concentration out from the combustion chamber is what we want to find. Remember, in this system itself, there are two terms. One is the generation term and the other one is the depletion term. So for the generation term, we can input it as plus 0.3 moles per hour. Now remember, when we do any mass balance equation, we must make sure that all the units are consistent. So if you look at the first unit, if you were to cancel out the liter, you will get mole per minute. The second one here, your C out will definitely be in terms of mole per liter. So if you were to cancel out, you get mole per minute, so it's consistent. But the third term here, you have moles per hour. So what you need to do is, you need to convert this hour to becomes minute. So you divided by 60 for this third term here. Now then, don't forget there's the depletion term. So your depletion term will be K value, which is given as 0.22 per hour, multiply by the concentration out, and don't forget your term V. So the volume in this case was given as 12 meter cube. Now don't forget to check your units. So in this case, you can see that your concentration out will definitely be in terms of mole per liter. So remember, we want to change all the units to be consistent for each of this term. So the unit must be moles per minute. So in this case, you must make sure your meter cube and your liter get cancelled off, and your hours must be converted to minutes. So you want to convert from your meter cube to your liter. So therefore, your 1 meter cube is equals to 1000 liter. So you convert it, multiply by changing your hours to become minute. Right? So if you were to solve this, your answer for the concentrations out from the combustion chamber will be 7.81 times 10 to the power of negative 5 moles per liter. Question 2. Question 2 requires you to use your Arrhenius equation. And remember, Arrhenius equation will be provided in the examination if it's required. Similar to your universal rate constant, it will be provided in the examination if it's required. With that, you are supposed to derive the equation for K1 over K2, because this will not be provided in the examination. So then you will get EA over RT1 divided by A exponential negative EA over T2. Your A and A can cancel, so therefore if you were to derive it, your K1 eventually will be equals to the following equation. Now input all the values into the equation. You can therefore solve that K1 over K2 is equals to 0.045. You must be very careful to ensure that your K1 must correspond with T1 and your K2 must correspond with T2. Question 3 is very simple. It states that 1 liter per minute of liquid containing A and B, given that the concentrations of A initial is equals to 0.1 mole per liter, concentrations of B initial is equals to 0.01 mole per liter. This stream flow into the CSTR of volume 1 liter, and the materials react in a complex manner. The outlet stream from the reactor contained A, B, and C. So the concentrations of A at the output of the reactor is 0.02 mole per liter. Concentrations of B at the output of the reactor is 0.03 mole per liter. Concentrations of C at the output of the reactor is 0.04 mole per liter. Now all you have to do is to find the inlet and outlet molar flow rate of A, B, and C, and eventually find the conversions of A in the CSTR. Now in the formula, you can find that the molar flow rate, in this case let's call it F, is equals to the volumetric flow rate multiplied by the concentrations. Therefore, in this case, it's very simple. If you want to find the molar flow rate of the stream A in the initial condition, all you need to do is to take the concentrations in the initial conditions multiply by the volumetric flow rate, in this case 1 liter per minute, and then you will get an answer of 0.1 moles per minute for the molar flow rate of your initial concentrations A. Molar flow rate of initial concentration B, the same thing, and you will get an answer of 0.01 moles per minute. So do the same for the outlet concentrations, and you will get the molar flow rate of A at the outlet to be 0.02 mole per minute. The molar flow rate of B at the outlet will be 0.03 moles per minute. The molar flow rate of C at the outlet will be 0.04 moles per minute. Now with that, you can now find the conversions of A. To find the conversion of A, the formula is given as the concentrations of A in the outlet of the system minus the concentrations of A at the output divided by the concentrations of A at the initial. So it is given as 0.1 minus 0.02 divided by 0.1, and therefore you will get a conversion of 80%. Question 4. A CSTR with a species A undergoes an elementary first-order irreversible reaction A to form B, and the K value is given as 0.045 per second. The conversions of A in this system is given as 70%. And you are supposed to find what is the residence time tau of reactant A in this CSTR. So using your basic mass balance equation for your CSTR, but in this case, I try to remove the V from the reaction term by dividing the equation throughout by V, the volume. And then with proper assumptions such that steady state dCA dt equals to 0 and the flow rate in equals to the flow rate out, I can then rearrange the equation as such. So with this, I can then solve because my tau value or the residence time is equals to V over Q. Therefore, Q over V will give me 1 over tau CA naught minus Q in equals to Q out, so 1 over tau CA. And then my reaction term will be negative 0.045 per second multiplied by the concentrations of A. With that, I can then rearrange my equation where I will get this equation. And then I try to rearrange it a little bit more. So I want to get my tau, because I want to find my residence time, so I want to find my tau. So essentially, I bring my tau over to the equal sign. So then all I need to do is to bring this term over to the opposite sides of the equal sign. So then I will get Ca0 minus Ca divided by 0.045 concentrations of A. Now then, it is given that the conversion Xa is 70%. So Xa is Ca0 minus Ca divided by Ca0. This gives you 70% or 0.7. Therefore, you can calculate that your Ca will be equals to 0.3 Ca0. So then I can then input this into the equation Ca0 minus 0.3 Ca0 divided by 0.045 multiplied by 0.3 Ca0. With that, you can then solve it to find that the tau in this case will then be equals to 51.8 seconds. Lastly, question 5. A CSTR with a residence time of 1.1 hours contains pollutant A that decomposes via a second-order irreversible reactions. The K value in this case is given as 0.009 per minute. If the exiting concentrations of pollutant A from the system is given as 40 moles per meter cube, determine the conversions of pollutants A. So similarly, you have to first set up your mass balance equation. So with your basic mass balance equation and your appropriate assumptions at steady state where dCA dt equals to 0, you can then derive the equations to be as follow. So input all the values that was given in the question. Tau value given as 1.1, concentration Ca0 is unknown, minus, again tau value 1.1, concentrations of pollutant A exiting from the system is given as 40, minus the K value is given as 0.009, but it is in terms of per minute, so therefore do not forget to convert it into per hour because you want all the units to be consistent. So if you were to convert it, you will get 60 multiplied by 60 minutes is to 1 hour. Now then, lastly, multiply by your concentration that is given as 40 square. So if you were to solve it, your answer for Ca0, the initial concentrations of pollutant A, will be 990.4 moles per meter cube. Now with that, you can then solve for the conversion using the formula Ca0 minus Ca divided by Ca0. Input all the figures that you know into the equation. You will get an answer of 95.96%. Now this is not the only way that you can solve this problem. So I'm going to show you another way in the next slide. For this second method, you will still need to use your basic mass balance equation with proper assumptions of steady state. So then, you will derive to get the following equation. Now with that, you can now convert your Ca0 to another formula so that you do not have to separately derive it. So it was given that Xa is equals to Ca0 minus CA over CA naught. So if I want to make CA naught my subject, I will be able to get the following equation. CA naught XA is equals to CA naught minus CA. So let's bring CA over to the other side of the equation to make it positive. I will get CA equals to CA naught minus CA naught XA. Let's take out the common factor, which is CA naught, 1 minus XA. So you know that CA will be equals to CA naught 1 minus XA. Or alternatively, you can also say that your CA naught is equals to CA 1 minus XA. So in this case, if I were to put this equation back into my original equation here, this is what I will get. So with this, I will then input all the values that I know into the equation. So I know that my tau is 1.1, concentration of CA is given as 40, 1 minus XA, minus, similarly, 1 over 1.1 multiplied by 40. K value in this case is given as 0.009, but I need to multiply by 60 to convert it into hours. So it becomes 0.54 per hours, and multiply by the concentrations of A at the outlet square. So if you were to solve this equation, then you can very quickly find that the conversion of A would then be equals to 0.956 or 95.6%. So this answer is comparable to the answer that you have gotten previously. We have come to the end of tutorial 7. Thank you for watching.